Okay, let's unpack this. We have a monumental task today.
We really do.
We are diving into the life and work of Vera Florence Cooper Rubin, the American astronomer whose revolutionary observations didn't just tweak the existing model of the universe.
No, not at all.
She proved that 90% of it was missing.
It is the ultimate scientific disruption. I mean, the New York Times described her impact as ushering in a Copernican scale change in cosmological theory.
And that's not a phrase you toss around lightly.
Not at all. Copernicus, he moved Earth from the center of the universe. Vera Rubin revealed that the fundamental gravitational scaffolding of our galaxies is made of something completely invisible to us.
And that shift from a universe we thought was defined by light and visible matter to one dominated by the unseen. That's the core of our mission today. We have sources detailing her challenging, decades-long career. We need to trace the specific, shocking evidence she provided on galaxy rotation rates, how that created the galaxy rotation problem, and why her meticulous data basically forced the scientific community to accept the existence of dark matter.
Precisely. And we're going to cover not just her science from being this controversial grad student to receiving the National Medal of Science, but also the significant institutional hurdles she had to overcome.
Right.
Her influence really extends beyond astrophysics into that necessary, arduous struggle for gender parity in science.
And of course, we have to talk about the Nobel Prize.
Oh, yes. The persistent, highly debated question of the Nobel snub, which, it speaks volumes about how scientific recognition is granted, or in this case, sometimes withheld.
That sounds like a deep dive worth every minute. For you, the listener, this is a shortcut to understanding one of the most important scientific figures of the last century. So let's start by establishing the intellectual engine that started it all, her early life and her refusal to accept the status quo, both in physics and in the academy. So Vera Florence Cooper was born in Philadelphia in 1928. Her family were Jewish immigrants from Eastern Europe. Her father, Pete Cooper, was an electrical engineer.
And her mother, Rose Applebaum, was a huge source of support for her early interests.
And then they moved to Washington, D.C. in 1938. And it was there in D.C. that the spark really ignited.
She was just 10 years old. 10. And she's watching the stars from her window. And that curiosity, it just became this consuming passion.
Right.
And what stands out in the sources is the supportive but also rigorous environment her parents created. Her dad helped her build her first telescope.
It's the one made of cardboard, right?
Yeah, a crude device made out of cardboard. And he helped her plot the tracks of meteors. So this wasn't just some casual hobby. This was systematic observation from the very beginning.
And she seemed to have this advanced philosophical take on science, even as a kid. There's that quote where she remembered being more interested in the question than in the answer.
I love that quote.
Me too. And she decided early on that we inhabit a very curious world. That phrase, more interested in the question, it's so revealing because her entire career was spent focusing on the weird stuff, the discrepancies and anomalies that other scientists either overlooked or just dismissed.
Exactly. She was drawn to the gaps in our knowledge, but that innate drive, it ran headlong into the rigid gender roles of the 1940s.
Oh, absolutely. She graduated from Coolidge Senior High in 1944, but not without that infamous encounter with a science teacher.
A high school teacher, mind you. He told her she should just abandon her plans for physics and astronomy and become an artist instead.
Just become an artist.
Yeah. The assumption was that women simply didn't belong in the hard sciences. It was just not a thing.
It's chilling to think how easily she could have been steered away. Thankfully, she just ignored him.
She did. And she enrolled at Vassar College. Vassar was an all-women's school at the time, which maybe ironically provided this protective environment for her to flourish away from the male-dominated university settings.
And Vassar had this history, right? With astronomy.
It did, a deep connection. It was associated with Maria Mitchell, the pioneering 19th century astronomer. So that heritage must have been incredibly inspiring for her.
And Rubin didn't just attend, she excelled. When she got her Bachelor of Science in Astronomy in 1948, she was the only graduate in that field that year.
The only one. She was already charting her own course.
But the moment she tried to get to the next level, the institutional barriers just slammed shut. She applied for graduate studies at Princeton.
Princeton, the absolute pinnacle of theoretical physics and cosmology at the time.
And what happened?
She was flatly barred due to her gender.
Not because of her grades or anything. Just
because she was a woman. It wasn't an oversight or a lack of space. It was explicit policy. And the sources note that this discriminatory policy at Princeton, it persisted until 1975.
1975.
Yeah. Think about the gravitational pull of an institution like that, the resources, the minds, the connections, and how many brilliant careers were just fundamentally altered or cut short because of that one policy.
It's a huge setback. But instead, she goes to Cornell for her master's.
Yeah.
Her future husband, Robert Joshua Rubin, was a physics grad student there.
And the astronomy department there was small, but being so close to pure theoretical physics, that turned out to be a huge unexpected advantage.
An immense advantage, yeah.
Even though she wasn't focusing on these areas at first, she was taking courses and breathing the same intellectual air as these giants. She studied under future Nobel laureates like Hans Bethe and Richard Feynman. So this immersion in cutting-edge quantum mechanics and advanced theoretical physics, it basically gave her the tools and the intellectual rigor she needed to challenge fundamental Newtonian mechanics later in her career.
So let's pivot to her master's research, because this is where she first showed her incredible knack for finding patterns in galactic motion that, just defied the textbooks.
Right. Working with Martha Carpenter, she studied galactic dynamics and found these observations that deviated from the standard uniform cosmic expansion, the Hubble flow.
So Hubble flow is the idea that all galaxies are moving away from us, and the farther they are, the faster they go. It's supposed to be smooth, uniform.
Exactly. But Rubin's observations, they revealed these peculiar motions deviations from that smooth expansion. She hypothesized an orbital motion of galaxies around a specific pole in the sky.
Now, her specific conclusion about that orbit was later disproven, I think.
It was. The exact nature of it, yes.
Yeah.
But the idea that galaxies were participating in these peculiar non-uniform movements, that was revolutionary.
So the general idea was right.
Absolutely. The general conclusion was correct. Large-scale streaming motions exist. This research provided the earliest observational evidence suggesting the existence of the supergalactic plane, a massive, flattened structure of galaxies stretching hundreds of millions of light years.
But in 1950, that was basically heresy.
Oh, completely. Astronomy was still just grappling with the concept of the expanding universe. The idea that there were massive, structured gravitational movements on top of that expansion was just, it was too much for the establishment to swallow.
And this brings us to the famous anecdote, the 1950 American Astronomical Society meeting, which just perfectly illustrates the dismissiveness she faced.
It's a remarkable story. She was only 22, presenting these incredibly controversial findings. She wasn't even a member of the society.
And there was more to it, right?
Oh, yeah. The compounding drama. She had given birth to her first child just 3 weeks before. So she has this monumental scientific idea, and she's dealing with this intense personal circumstance at the same time.
And the reception to her talk.
The sources say it was met with universally negative feedback. Her presentation was rejected for publication. The science was completely dismissed.
But the story of it made the news.
Yes, but they focus on the wrong part. The Washington Post ran a front-page headline that completely marginalized the science. It was, "Young mother has own theory of universe."
Ugh, that just encapsulates the whole problem for women scientists back then. Their revolutionary intellectual work was constantly overshadowed by these domestic labels.
If the intellectual community won't publish your work and the media focuses on your baby, how do you sustain the momentum you need for a scientific breakthrough?
You persist.
You persist. She moved on to Georgetown for her PhD, studying under the brilliant but equally unorthodox George Gamow, one of the founders of Big Bang cosmology.
And her dissertation there, completed in 1954, it continued her pattern of finding structure where everyone else saw randomness.
That was her work on galaxy distribution, correct?
Yes. The prevailing scientific consensus was that the universe was homogeneous and isotropic on large scales, meaning galaxies were just randomly, uniformly distributed.
Like sprinkles on a cake.
Exactly. And Vera Rubin analyzed the available data and concluded the exact opposite. Galaxies clumped together. They formed structures.
So she was seeing the seeds of what we now call the cosmic web filaments, sheets, and voids, 2 decades before anyone else took it seriously.
Precisely. And her dissertation was ignored, neglected by the field for nearly 20 years because it contradicted that foundational principle of homogeneity.
It took until the 1970s and 80s with massive sky surveys and computational power to confirm beyond a shadow of a doubt that galaxies organize into these vast, structured clusters and superclusters.
It's incredible. By the time she was 26, Rubin had produced 2 earth-shaking ideas, peculiar galactic motion and galaxy clumping, and both were rejected by the establishment.
It just shows an immense intellectual fortitude to keep questioning the basic assumptions of cosmology. And that persistence, it leads us directly to her monumental dark matter breakthrough.
So after her PhD, Rubin spent several years in teaching roles at Montgomery College and Georgetown. These early academic positions, they were complex, right? Helping her balance career and family, but they weren't always at the cutting edge of research.
No, but that changed, and it changed in a big way in 1965 when she joined the Carnegie Institution of Washington's Department of Terrestrial Magnetism, or DTM.
And Carnegie became her perfect scientific home.
It really did, especially because it paired her theoretical and observational genius with technical engineering excellence. She met the instrument maker, Kent Ford, who became her indispensable longtime collaborator.
And the breakthrough observations they made were truly a synergy of observation theory and this advanced technology.
Yeah, let's talk about the tech. Their work used Ford's image tube spectrograph. For you, the listener, why was this piece of equipment so revolutionary in the 1960s? Why couldn't they have done this study a decade earlier?
It's a critical detail. To figure out the velocity of anything in space, you need to analyze the light it emits, specifically the Doppler shift.
Right. Light from an object moving away gets redshifted. Moving toward us, it's blue shifted. The problem with studying galaxies, especially the stars and gas at their outer edges, is that they are extremely dim.
So traditional spectrographs just couldn't collect enough photons to get a clear spectrum.
Not in a reasonable amount of telescope time, no. You'd be staring for weeks.
So the image tube spectrograph was like a massive light amplifier.
That's a perfect way to put it. It was a crucial image intensifier. Ford's design could gather that faint light from the peripheral regions of a galaxy and intensify the signal so that a measurable spectrum showing those critical velocity shifts could be obtained.
So this tech let her peer into the faint outermost realms of galaxies.
Exactly where the most important cosmic mystery was hiding, completely unseen by traditional methods.
But before they got to the rotation problem, they collaborated on the Rubin-Ford effect, published in '76.
Yeah.
This was another major finding about galactic motion, basically a refined look at her controversial master's thesis from 25 years before. What was the core discovery here?
They studied spiral galaxies, including Andromeda, our nearest big neighbor, and the Rubin-Ford effect documented this apparent anisotropy, a non-uniformity in the expansion of the universe on a scale of about 100 million light-years.
So they found that our local group of galaxies seemed to be streaming or moving toward a specific distant point in space.
Yes, overriding that smooth Hubble expansion. So even on those vast scales, the universe wasn't expanding like a perfectly smooth balloon. It was being tugged by something enormous.
And I'm guessing this was also controversial.
Oh, highly controversial. Again, the idea that galaxies had this large-scale peculiar motion, this large-scale streaming, it implied the existence of massive unseen gravitational structures influencing huge cosmic volumes.
And it was initially dismissed.
Yet again by leading astronomers. But the observation was solid, and later research confirmed this gravitational pull, eventually leading to the identification of massive structures like the Great Attractor. It just reinforces the pattern. Rubin looked for motion in the periphery, and that motion always pointed to mass she couldn't see.
And that search for unseen mass led her directly to the most famous part of her career, the galaxy rotation problem.
Right. She shifted her focus from large-scale streaming to the internal dynamics of individual spiral galaxies. This is the centerpiece of the deep dive. She started by looking at the rotation curves.
That's the graph showing the orbital speed of stars versus their distance from the galactic center.
Exactly. And to understand how revolutionary her finding was, we have to first establish the textbook expectation based on classical Newtonian physics.
Okay, let's break that down. If you look at a solar system or a galaxy, most of the visible mass, the stars, the gas clouds, it's all concentrated in the center, in the bulge.
Correct. So Newtonian physics predicts that for objects orbiting a central mass, like planets around the sun, the speed has to decrease as the distance increases.
Right, the analogy we all know. Mercury zips around the sun super fast,
Yeah.
but Pluto, out in the boonies, is moving at a relative crawl because the sun's gravity is much weaker out there.
That's the logic. And if you apply that to a galaxy, the stars way out in the spiral arms should be moving much, much slower than the stars near the core. The rotation curve should drop steeply, it should fall off once you move past the visible edge of that central bulge.
That is the crucial expectation.
But using Ford's supersensitive spectrograph, which let her look at those faint outermost stars and gas clouds, Rubin observed something entirely different.
She observed flat rotation curves.
Flat rotation curves.
What does flat actually mean here? That the orbital speed of objects at the galaxy's edge was the same as the objects near the center.
The same or nearly the same. It was a profound fundamental contradiction of everything we thought we knew.
So if the speed doesn't drop off, that means the gravitational influence, the total mass, must keep increasing as you go further out.
Yes, linearly, out to the very limits of her observations. The stars on the edge were moving way too quickly for the galaxy to be held together only by the gravity of the stars and gas we could see.
Wait, if the stars are moving that quickly and the visible gravity isn't enough to hold them, shouldn't the whole galaxy be flying apart?
It absolutely should. I mean, if ordinary visible matter were the only source of gravity, the centrifugal forces from that rotation speed would just fling the stars into intergalactic space.
But they don't.
But they don't. The fact that spiral galaxies are clearly stable, rotating structures led to the one unavoidable conclusion. There must be a vast amount of unseen, undetectable mass providing the necessary gravitational glue to keep everything bound together.
And this became the galaxy rotation problem.
Mm-hmm.
So let's talk about the sheer magnitude of this discrepancy.
Yeah.
How much extra invisible mass did her measurements require?
Her calculations, which were confirmed across dozens and dozens of spiral galaxies in the following years, showed that the visible matter accounted for only a tiny fraction of the total gravitational mass.
So this is a tiny fraction.
A tiny fraction. Galaxies must contain at least 5 to 10 times more mass than we can observe directly. And this led to the concept that every spiral galaxy is encased in a massive, invisible halo of something we now call dark matter.
So we were looking at the galaxy thinking we saw the whole structure, but in reality we were only seeing the glowing 10%. She introduced us to the 90% that was invisible.
That is the Copernican scale change.
It is.
Yeah.
Now, while Rubin provided this first persuasive, robust observational evidence, it's important to contextualize this idea. The theory of missing mass wasn't entirely new.
Right, you're referring to Fritz Zwicky in the 1930s.
Exactly.
Yes. Zwicky, a brilliant but famously idiosyncratic Swiss astronomer at Caltech, had observed similar discrepancies when looking at the motion of galaxies within the Coma cluster. He found the individual galaxies were moving so fast that the cluster should have just disintegrated. He's the one who coined the term Dunkel Materie dark matter.
So if Zwicky suggested this decades before, why was his work dismissed? And what made Rubin's data so fundamentally different that it just couldn't be ignored?
There are a few key reasons. First, Zwicky was looking at galaxy clusters, which are incredibly complex systems. Rubin was looking at individual spiral galaxies, which are simpler rotating systems, and that allows for a much cleaner gravitational calculation.
Simpler system.
Second, Zwicky's methods and measurements were often considered preliminary or rough, and his abrasive personality didn't really help win converts.
I've heard stories.
But most importantly, Zwicky saw discrepancies in large clusters, but Rubin's flat rotation curves showed the deficiency of visible mass was a universal characteristic of every single galaxy she observed. It was a local, repeatable, and quantifiable problem that demanded an immediate answer. Her data, powered by Ford's spectrograph, was just. It was meticulous and undeniable.
So once Rubin established this mountain of evidence, the field finally had to grapple with the reality of this non-baryonic matter, the dark stuff.
And the confirmations came rapidly.
Using completely independent methods, which is the gold standard of scientific validation.
Exactly. For example, radio telescopes were used to detect the 21-centimeter hydrogen line.
Okay, what exactly does that measure, and how did it confirm Rubin's optical data?
The 21-centimeter line is a specific wavelength of radio emission produced by neutral atomic hydrogen gas. Now, crucially, this gas, while still ordinary matter, often extends much further out into the galactic halo than the visible stars do.
So it lets you see even further out.
Much further. By mapping the Doppler shifts of this neutral hydrogen, astronomers could measure the rotation curves far beyond where Rubin's optical spectrograph could reach.
And did those rotation curves finally fall off at those extended distances?
Nope. The 21-centimeter data showed that the rotation curves remained flat even further out, confirming the need for this expansive, massive gravitational halo.
And then there were other methods, like gravitational lensing.
Yeah, where the gravity of unseen mass visibly warps the light from background objects. That provided visual proof of the dark matter halos surrounding galaxies and clusters, exactly where Rubin's mathematics predicted they should be.
Now, despite this overwhelming evidence, did Rubin herself immediately commit to the existence of a new type of particle to dark matter?
That's a very important nuance. Rubin, ever the rigorous empiricist, kept an open mind. While her data was the foundational pillar of the dark matter theory, she remained cautious about the ultimate explanation.
So she was still prioritizing the question over the convenient answer.
Absolutely. She understood that her measurements indicated a breakdown in our understanding of gravity or mass distribution. She and her contemporaries explored alternative models like modified Newtonian dynamics or MOND.
Which suggested that gravity might just operate differently at extremely low accelerations, eliminating the need for exotic new particles.
Exactly. She remained committed to the data, regardless of what theoretical framework it supported. The goal was to solve the discrepancy, whether through new physics or new matter. That's true scientific integrity.
And before we move on to her legacy, she had one more groundbreaking discovery related to galactic motion that shook up how we think galaxies evolve: the phenomenon of counter-rotation.
Yes, another classic Rubin observation. She studied galaxies like NGC 4550 and discovered that a significant population of gas and stars were moving in the exact opposite direction to the rotation of the rest of the galaxy.
That seems impossible. It flies directly in the face of the prevailing theory that galaxies are simple, unified spinning disks.
It was startling evidence. The discovery of counter-rotation provided the first clear observational proof of violent galactic paths. It demonstrated that galaxies grow through accretion and mergers, where material like gas clouds or even smaller satellite galaxies can be absorbed and incorporated, all while maintaining its original opposite angular momentum.
So it challenged the simplistic, uniform evolution models.
And confirmed the chaotic, dynamic nature of the cosmos. That observation immediately became essential to modern galaxy formation theory.
Vera Rubin's life really does have these two parallel, equally important narratives: discovering the dark universe and this lifelong fight against institutional exclusion.
Absolutely. Her story is littered with these anecdotes that just perfectly encapsulate the systemic sexism of 20th century science.
These weren't just personal affronts. They were systemic roadblocks designed to impede career advancement.
Right. Let's start with the Palomar Observatory incident in 1965. Palomar was, and still is, a critical national research facility. Gaining observation time there is the lifeblood for professional astronomers.
And when she applied to be the first female astronomer permitted to observe there,
She was reluctantly granted access, but the excuse they gave for limiting her time was just absurd.
it was a bathroom, right?
The bathroom. They informed her that the facility lacked a women's bathroom. And this was often a deliberate institutional strategy. If you don't provide the basic facilities, you can deny access and claim it's a logistics issue, not discrimination.
I remember reading about how she handled that.
Yeah.
It's the perfect snapshot of her practical determination.
Oh, it's classic. According to the account from Carnegie president Eric Isaacs, Rubin was not going to let plumbing stop science.
Not a chance.
She found the little stick figure sign on the men's room door, she cut out a small paper skirt, and she taped it to the figure. Then she just declared, now you have a ladies' room. Problem solved. Then she went right to work. It shows that unstoppable mentality. When you're faced with absurdity, you find the simplest, most direct solution and get back to the science.
But the institutional bias was so much more pervasive than just bathroom access. It extended deep into her academic journey at places like Georgetown.
Oh, yeah. During her PhD studies, the policies were so archaic that she was barred from meeting her advisor, George Gamow, in his campus office, because women were not permitted in that particular area of the building.
You're kidding me.
Nope. This meant she often had to conduct essential research discussions in hallways or non-academic spaces. And you have to think about the insidious cumulative effect that has. It's a constant signal that you don't fully belong, that your presence is inconvenient, and that your work is secondary to these institutional rules.
And motivated by these constant battles, she spent the rest of her life trying to ensure the path was smoother for the women who followed her. She became this tireless advocate and mentor.
She made sure to provide the support and encouragement that she often lacked. She passionately encouraged girls to pursue astronomy, making science feel desirable and fun, as her own children recalled.
She was a crucial mentor to generations of female astronomers, people like Sandra Faber and Rebecca Oppenheimer.
Yes, helping them navigate the challenges of balancing family life and a demanding research career. And when she was finally elected to the National Academy of Sciences in 1981, she immediately used that institutional leverage to push for reform.
She was only the second woman astronomer ever elected to the nest.
Right after Margaret Burbage. And rather than taking the honor lightly, she campaigned relentlessly from the inside. She pushed for more women to be elected, to be included on prestigious review panels, to be represented in academic searches.
And our sources highlight her deep personal frustration with how slow that change was.
Yeah, she said she found the continued low number of women elected to the NAS to be the saddest part of her life.
Wow. That statement, coming from someone who fundamentally redefined the universe, it carries immense weight.
It speaks to the ongoing, essential nature of that fight.
Let's also touch on her success in raising her own family, because it provides such a profound counter-narrative to the idea that women have to choose between science and family.
It is truly remarkable. She married Robert Joshua Rubin in 1948, and she completed her PhD while already having 2 children. She had her 4 children over a period that spanned her master's and PhD years. I mean, that's just an incredible feat of endurance and organization.
And the outcome for her children is, it's statistically unbelievable given how hard it is to pursue advanced degrees in STEM fields.
It is. All 4 of her children earned PhDs in the natural sciences or mathematics. You have David and Alan, who became geologists, Judith, who followed her mother into astronomy, and Carl, who became a mathematician.
That's incredible.
Their collective success is a powerful testament to her ability to model a scientific life as something enjoyable and accessible, defying all the social expectations that she faced.
Our sources also delve into her personal philosophy on the relationship between science and faith. How did she, as a Jewish woman immersed in cosmological discovery, reconcile those two domains?
She saw no conflict at all. She maintained a very clear separation between the moral framework of religion and the empirical inquiry of science. She explained, "In my own life, my science and my religion are separate. I'm Jewish, and so religion to me is a kind of moral code and a kind of history, while science," she said, "helps us understand our role in the universe."
So for her, science was the mechanism for discovery.
And religion provided the necessary moral compass for how that knowledge should be pursued.
Okay, let's move to the point of contention that shadows her recognition.
Yeah.
The Nobel Prize controversy. She passed away in December 2016, and almost immediately, the debate about the ultimate institutional snub began.
It remained perhaps the most significant omission in modern science prize history. Rubin is widely thought to have been snubbed for the Nobel Prize for her definitive work establishing the need for dark matter.
Prominent physicists like Lisa Randall and Emily Levesque have publicly stated this was a glaring oversight.
A glaring oversight, yes.
So when we look at the discussion, what are the primary arguments for why the Nobel Committee might have failed to award her, even given the significance of the discovery? Was it just gender?
Well, gender certainly plays a historical role, especially given her lifelong battles. But observers also point to the nature of the discovery itself and the timing. Dark matter is still a placeholder. It's the discovery of a lack of predicted mass, which requires a new exotic particle that remains hypothetical and undiscovered. The Nobel Committee often prefers to award discoveries of definitive concrete phenomena or particles.
So they might have been hesitant to award the prize for a discovery that's defined by an absence, even if that absence redefined cosmology.
That's one theory. Another is the complexity of choosing who should share the prize wiki, who proposed it early, or the later researchers who confirmed the nature of the halos through lensing.
The timing issue.
Right. But the overwhelming consensus in the astronomical community is that her meticulous observational confirmation of the flat rotation curves provided the undeniable proof that spurred the entire field forward. That singular contribution, regardless of who else might have shared it, was certainly worthy.
And regardless of their rationale, she's continually listed among the women of the 20th century whose work profoundly impacted physics but went unrecognized by Stockholm.
Yep. But despite that omission, the scale of her enduring recognition is truly global. It's even cosmic.
Yes, the honors she received post-mortem are a true reflection of the magnitude of her impact. In 2019, the Large Synoptic Survey Telescope, a major new facility in Chile, was officially renamed the Vera C. Rubin Observatory.
And it's an observatory specifically designed to study dark matter and dark energy.
That is the ultimate fitting tribute, a state-of-the-art facility generating unprecedented amounts of data carrying her name.
And that observatory, located in Cerro Pichon, Chile, it began producing its first survey images by April 2025. It means her scientific pursuit is literally built into the infrastructure of future cosmology. Her name will be attached to the data that seeks to solve the very mysteries she revealed.
And beyond the observatory, her legacy has been cemented across various domains.
She has a Martian area named in her honor, the Vera Rubin Ridge. Asteroid 5726 is named Rubin.
Domestically, the U.S. Mint recognized her importance by honoring her on a 2025 U.S. quarter.
Which is fantastic. And significantly, the tech sector has also recognized her impact. NVIDIA, the massive computational powerhouse, named their next-generation data center accelerator CPU and GPU systems after her, Vera and Rubin.
That's a hardware-level recognition.
Yeah.
That's amazing.
It signifies that the massive computational tools required to model the universe she revealed and process the data from the very observatory named after her will be powered by processors carrying her name. It's an influence that permeates every single layer of modern science.
Her influence is inescapable.
Because her discovery is inescapable. She took the universe we thought we understood and demonstrated that the foundations, the invisible architecture, were far grander and stranger than we had ever conceived.
This has been an incredibly insightful deep dive. We've established that Vera Rubin's journey wasn't merely about finding a new fact, but about fundamentally changing the questions astronomers ask. If we synthesize the three core takeaways. First, we saw the incredible power of meticulous observational data, those flat rotation curves, which overturned centuries of classical physics. Second, we recognized the revolutionary, paradigm-shifting conclusion that dark matter dominates the cosmos.
And third, her tireless, essential advocacy for women in science, making sure the path was clearer even if she had to draw the bathroom sign herself.
Her career is the ultimate example of intellectual independence and perseverance against overwhelming odds, both scientific and social.
It is. And she distilled her philosophy into this remarkable statement that serves as a final thought for us all. Don't let anyone keep you down for silly reasons, such as who you are. And don't worry about prizes and fame. The real prize is finding something new out there.
I love that. She dedicated her life not to gaining accolades, but to the pure, unadulterated joy of discovery.
That's it, exactly.
That is a phenomenal summary of a groundbreaking life. So what does this all mean for you, the listener, and for the future of cosmology?
Well, we have to remember that Rubin's career began with these highly controversial ideas. Peculiar motions, clumping that were dismissed for 20 years before becoming foundational.
Right.
Her major breakthrough on dark matter took decades of persistence to prove. Now, the magnificent Vera C. Rubin Observatory, specifically designed to catalog the structure of dark matter and dark energy, is generating unprecedented volumes of new data.
So here's the provocative thought.
If her observations twice forced a Copernican scale change by finding motion and structure where none was expected, we should expect the same intellectual disruption again. The next wave of discovery, powered by the data from the observatory bearing her name, may reveal patterns or discrepancies that, yet again, force us to challenge our most fundamental assumptions about the nature of gravity and mass. The universe, thanks to her, is still holding secrets we haven't even begun to formulate questions about.